So this is my talk, mercifully not about ORMs, but about the I/O monad, and specifically what it is and why we want it and what that means on the JVM. So if you're like me, you've probably done something like this at some point in the past, which is, sort of made the claim that the I/O monad is just boilerplate from Haskell. It's sort of this unnecessary thing that we do mostly because Phil Wadler just says we should do it, and there's no other purpose behind it. I have come to realize over many, many years of much sort of bloodying my nose against this, that this is sort of nothing could be further from the truth. The I/O monad is really actually about effects. And it's really actually a profoundly pragmatic and important thing. It's very, very, very useful. It helps us solve these problems. Hopefully by me relating this, you will be able to bloody your nose somewhat less. Or at the very least, bloody your nose on different walls than I did. So effects, what is an effect? Well, an effect is something that you just can't do twice, right? So writing to the database, reading from standard input, incrementing a counter, et cetera, right? Anything with sort of state that you mutate in place. These are things that you really care about. You're doing it exactly once, and you're doing it in exactly this place. Effects are tremendously hard to test, okay? Now, I guess I've found this more and more as my apparently 5-year career has proceeded, is that testing really is kind of the heart and soul of writing decent software, right? If you can write good tests, then you've probably written relatively reasonable software, and if you've written good tests, then your software is probably comparatively bug-free. Effects make this very, very, very difficult. Effects make concurrency very, very, very difficult. You have a really hard time. The hardest problems in concurrency are oh, I've got this shared resource that two things are trying to change something about at the same time, and you have to coordinate between them. But simultaneously, if you don't have effects, then concurrency is kind of pointless. There's really very few things that are concurrent problems that do not involve changing some sort of state. Just think folding at home is probably the best example of a non-effectful concurrency, but everything else is there. And effects also make refactoring hard. They make it very difficult for us to change things about our code. And so what I mean by that is something like this. So if you take this foo42 plus foo42, we would sort of want to factor out the method call here because it's redundant, and we want to change it into something like val x equals foo42, x plus x. But we can't do that, right? Because we don't know what foo is. Foo could be something nasty, like add to gauge or something like that, right? We don't actually know if it's modifying things about the system. These two could in fact be separate programs, which is actually, if you think about it, if you put aside sort of the biases that we all have from being indoctrinated by systems like Java, it's actually profoundly weird that these are not the same program, right? They really should be the same program, and effects are the reason that they're not. So really, we should find a way to get this property back, because I think this is something that's pretty intuitive. And we can do it by controlling our effects, by making them more constrained, more confined, turning them into data so that we can work with them. And the traditional way of doing that is with the I/O monad, right? So if we take this add to gauge function, and rather than having it return an int, if we have it return an I/O event, and we'll get to what this means in a bit, then we can sort of replicate our example from earlier where we have this for comprehension with sort of 2 add to gauges, and we can factor it out, and these are in fact the same program, right? The one on the left does the same thing as the one on the right. That seems like a good thing. Making code that's easier to parcel up and move around and things like that without worrying about the definitions changing, yeah, that seems like a benefit. So what the I/O monad does is it allows you to safely manipulate effects. And safe is not in quotes there. It's actually safer, right? And it does this by allowing you to build a description of the program that will be run, okay? You build a description, you don't build the running program, and later on it will be evaluated for you. Critically, descriptions can be changed, right? So we're reifying the effects in our program into some sort of data structure, and then we can manipulate that data structure before it gets evaluated. If any of you come from a Lisp background, this probably sounds a lot like code as data. Surprisingly, that's a really good idea. And the I/O monad is one of the ways in which we can achieve this in languages like Scala or Haskell. The IO monad allows us to separate the composition of our program from the declaration. So we can declare what it means to perform a particular effect, like what the definition of an effect is, separate from how we declare how it is run and how it's composed with other effects. And if this sounds like concurrency, then you're on the right track. This is exactly what concurrency is, right? Like as soon as you separate these things out, concurrency becomes very easy. It also sounds like dynamic scaling and other things that systems programmers care very, very, very deeply about. Back pressure and dynamic load recalibration and things like that. All of these things are separated composition. And you're controlling the composition of how your program behaves under load and in batch modes and things like that. By separating that out, you can get some really, really, really so profoundly important properties for systems, sometimes actually for free. Now, the obvious question to ask here is like, we say the IO monad. Why does it have to be a monad? Like, what's monadic about it? It doesn't look anything like list or option or anything like that. And the reason basically comes down to the fact that programs have to be sequentialized, right? Program actions have to be sequentialized. We care very much when we say print line hello, print line world, we care very much that it doesn't come out world hello, right? Like that's kind of important. Monads, it turns out, are the essence of doing things sequentially. Like literally, actually, the definition of sequentiality is a monad. And so if we want to say, well, hello happens before world, we can't even speak that sentence without having a monad. And this is what Philip Wadler's contribution to this space was, right? Like we all sort of remember him as introducing monads to Haskell, and he did. But he introduced them to Haskell precisely because of this realization that this sequentialization property was so powerful and so intrinsic. So here's basically what it looks like and why we know that this is true. So this is the monad type class in Scala. If you're coming from Haskell, you're probably like, why are there twice as many characters as there need to be? And the names, you can quibble at the names, right? Like I called it pure and flat map. You could call it bind and return. It doesn't actually matter. The interesting thing is that we've got two functions, one of which puts a value into the monad and the other of which composes two monads together. And we know that the composition of two monads must be sequential because of one very, very specific thing inside the middle of this type signature. Does everybody see it? It's right there. The A, right? The A. Where does the A come from? There's only one place the A can come from, inside the f of A, right? And the A is the only place where we can get an f of B, which is the thing that we return, right? So we have an A. We don't have an f of A or like some other thing like that. We literally have to get a bare A to feed to this function in order to get the f of B that we finally return. And this is a very, very powerful thing because it means that the f of A, the first parameter, must have evaluated before the second parameter, the f of B, can even be considered, because the f of B doesn't even exist until the f of A is done. So this is a strong sequentialization guarantee. It basically means that all monads have sequential composition. Monads are sequential composition. They are nothing else. And this argument, this sort of style of analysis is called parametricity. So if you hear that word like on Hacker News or something like that, this is what they're talking about, is arguments like this. And when you take this kind of reasoning to the extreme, you can get some very, very deep insights about your code just by looking at the generic types and saying, well, this has to come from there and this has to come from there, therefore like random property X holds. And that's a very, very powerful way to reason about software. But we were talking about the IO monad, and so we know that the monad is sequential. What does this actually look like in languages? Because like we're interested in what this is going to look like in Scala. Maybe we should look at what it looks like in Haskell. And it basically looks like this. Okay, so this is a trivial little Haskell program. We have a main function, which is of type IO of unit, and we just print line hello world. And this is a pretty typical thing in Haskell, right? All Haskell programs come back to IO of unit, right? Like all roads lead to IO. When you're going around and manipulating things in Haskell, right, you're calling out to network functions or you're like interacting with the CFFI, like all of that is going to be encapsulated in IO for you. So like you already are given effects inside of IO. The only way you can get an effect is like inside of the IO monad. And then conversely, like the only place for effects to go is like at the end of your program, you hand an IO to the Haskell runtime, and the Haskell runtime will evaluate that description. You cannot construct a new IO except using return. So this is just kind of like restating what I just said, right? Return takes a pure value and puts it into IO. That's the only way to construct an IO in Haskell unless the IO has been handed to you by a function like print Sterling. Concurrency is also, in Haskell, managed through the I/O monad. So this whole notion of like manipulating threads and things like that is handled inside of I/O. The platform does it for you, more or less. And similarly, like, concurrency as a whole, and this is going to be an important point for later, but concurrency as a whole in Haskell is a little bit different. You basically have a notion of green threading, right? So like Haskell doesn't even give you primitives for manipulating threads. It instead gives you primitives for sort of like forking things off and then joining at the end, like working at this very, very high level of abstraction, right? And that's basically the notion here, right? GHC is a very high level runtime. It does a lot of very high level things for us. It encapsulates things in I/O. It evaluates I/O for us. You know, it deals with things like threads and sort of encapsulates us from the nature of callbacks and such. And because the runtime is so high level, Haskell's I/O monad is really, really very simple. It basically only has two save functions, bind and return. Scala is a little bit different though, right? Because a Scala main function looks like this, which is not, like you can't really do anything with that, right? Like it returns unit. What does unit even mean? Well, I mean, I guess it just means it runs side effects. So like we can't make any parametricity arguments other than like it exists. So that's not really helpful. And Scala and Java like sit very closely together, right? There's no FFI between them. So even if Scala gave you the ability to encapsulate your effects quite easily, Java certainly doesn't. And you can call out to any Java function you want, and it might like manipulate the gauge, and you can't control that. We can run any effects we want at any time, even effects that we don't want, right? And the evaluation is eager. So if you say something like print line hello world, it's printing, like right the heck now. And you can't do anything about that, right? By default, there's no way for you to get in the middle of that process and say, hang on just a second, maybe we should talk about what it means platonically to print hello world. Haskell gives you that ability, Scala does not, by default. And also, Scala has these very low-level concurrency primitives, like synchronized and atomic reference and callbacks and threads and other things like that that are really, really, really complicated to get right and very, actually, like really low level, right? They're resources that have to be managed pretty carefully. If you look at sort of the JVM's notion of concurrency versus Haskell's notion of concurrency, it's a little bit like the difference between C's notion of memory and Java's notion of memory. Like, they're just completely differently layered worlds. And so, again, because the I/O monad is really about runtime and about the nature of the runtime and abstracting over that and providing descriptions to the runtime, clearly, the I/O monad on the JVM is going to have to look pretty considerably different than the I/O monad on GHC. So Scala runs on the JVM. It has native threads. It has explicit asynchronous I/O with this callbacks things. And we can't block things, right? So this is kind of an often overlooked property of GHC's green threading model is that like you just basically block things kind of all the time, right? You had like the fundamental primitive for bringing two threads back together in GHC is like an mvar, where you literally block and wait for some other thread to give you a value. That notion is entirely antithetical to the JVM, where threads are a very limited resource. You can only have a certain number of them. They're all GC roots. You can't block them. You can't throw them away. Like, there's a lot of very, very expensive things going on there. So we have to be much, much more careful about this stuff. And finally, again, this is another sort of difference in the runtime. The JVM doesn't have tail call elimination. So if you've been around the JVM for a while, you probably know that this is a thing that everybody wants, that everybody on the JVM team wants to add, but they can't because of a feature in Java 1.1. And we're sort of stuck with that for the rest of time. But because GHC has tail call elimination and we don't, that means that we have to care very deeply about the stack in a very explicit way, in a way that GHC does not. And so we want people to be able to write programs, ideally their entire program via composition, inside the I/O monad by the end of the world. Most interesting programs run forever. So clearly, we're going to have to care about the stack in some explicit way because we cannot take anything more than constant stack space. It has to be constant, no exceptions. Because if I'm running a program for 6 months, you can't accumulate stack at all in that time. So there's going to be a lot of things that are different about the I/O monad on the JVM, but there's a lot of things that are going to be the same, right? So it's still going to be a monad, great. It's going to manage stack safety for us. It's going to have different evaluation modes. You know, in Haskell, there's only one way to construct an IO monad with a pure value. And we should probably have that way in Scala. We should have it sort of be some sort of strict pure value that we've already computed, because strict computation is faster on the JVM than lazy computation. But at the same time, we still need to be able to get in the middle of like the whole print line hello world thing and capture that effect up so that we can evaluate it later. So we're going to need a way of constructing these things lazily, right? So have a lazy constructor to wrap effects up in I/O. And finally, we're going to need an asynchronous constructor, okay? Because callbacks, right? You know, in asynchronous programming, everything interesting that's going to happen with any real I/O framework in the JVM is going to involve callbacks. We want to be able to bottle that up inside of I/O, just like Haskell does for us with green threading. And all of this is just going to turn into sort of different constructors that produce the I/O monad. So this is definitely going to be considerably different than what we've seen before. So what possible candidates are there in Scala for implementing this style of construct? Well, one obvious one that's just baked into the standard library is future, right? But future, like, I mean, we've all used it. Like, some of us still use it. It has a lot of problems if you're trying to use it as an I/O monad. And the most obvious problem is that actions run eagerly, right? Remember that whole problem with, like, we say print line hello world, and it's already printing before we have a chance to stop it, right? Like, future does that, right? Futures run eagerly by default, and stopping that from happening is actually quite difficult to do. Future also memoizes results. So you can't take an action, define it, and then run it multiple times, like the whole add to gauge thing. That's actually a really, really, really serious problem that also can lead to memory leaks if you're not careful. But at a minimum, it certainly prevents us from, you know, having the, you know, the sort of program that we had before, right? So like if we take our example from earlier, where we have like x is add to gauge and then, you know, sequence the x twice, this is only going to add to gauge once if this is defined as a future. That seems wrong. So future just isn't good for this, right? It doesn't encapsulate asynchronous execution really much at all, which is funny because this is kind of the whole point of future, right? But the problem is that promise is a really leaky abstraction, right? You create one of these things, it's hanging out over here, it's completely separated from the future, maybe the future doesn't exist at all. Have you fulfilled the promise yet? Have you not fulfilled it yet? God only knows. Ask a function, maybe it'll tell you. Like, it's really like, they're just kind of like these completely separated things. They're not tied together very well at all. And that can lead to a lot of really weird bugs in your code. It's not very directly encoding the callback model. And finally, and this is really frickin' annoying, future will rewrite exceptions into wrapped things some of the time, not all the time. And so if you're using future, you basically have to like get exceptions back out of it and then look at those exceptions and see, are you wrapped? Are you maybe wrapped 2 times? I don't know. Ask. And then maybe you're not wrapped. And then like try to kind of deal with all of this weird non-deterministic boxing that may or may not happen depending on where an exception came from in your code. So this seems just sort of like unambiguously bad. So if you're using future as an I/O monad, stop. It doesn't work very well. But there are some other options. So Scalaz 7 has something conspicuously called I/O, which one would think would more or less satisfy our criteria. But unfortunately, it suffers from the limitation of being directly ported from Haskell in an extremely naive way. And it really doesn't support the features that we need at all. So Scalaz 7 I/O, it doesn't support asynchrony, like in any respect. There's no support for callbacks whatsoever, which is kind of a problem. And because of this, it encourages you to do things like block threads, right? So remember, I talked about mvar in Haskell. Like mvar, if you naively port it to the JVM, you're just going to like block a thread. Like you're literally just going to like block a thread and wait for a value from some other thread. And unlike on GHC, that is not cheap. So, and Scalaz 7 just kind of pushes you to do this. It only has a lazy effect capturing constructor, so you don't have the ability to lift a pure value strictly into the I/O. And remember, strict execution is much, much, much faster than lazy execution when you actually already have the value in your hand. So, you know, not having a strict constructor is kind of a pretty significant omission for something that purports to care about performance. And so as a consequence, Scalaz at 7.io is very, 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 very slow. And finally, it just basically provides no abstraction whatsoever. So it's ironic. So for a framework that's basically all about abstraction, this is a very, very, very concrete thing. And the only type class that it provides that characterizes its behavior is lift.io, which is basically this, right? So lift.io is like this super trivial thing that basically says, I don't know what your f is, but whatever it is, it has an io inside of it. That's not that helpful in practice. It seems like it would be helpful, but it's actually not. And there are no laws about it. There's certainly no attempt to define what it means to be an I/O in sort of an abstract sense, or any of the sort of operational laws that would surround that. So Scalaz at 7.io was written like 8 or 9 years ago, so quite some time. In about 5 years ago, they decided, oh well, let's take another crack at this I/O thing, and we'll call it task. Okay. So Scalaz at 7 has task, which is also an I/O monad, and then the name is longer, which is actually really, really annoying when you have to write this thing about 400 times a day. That's, I don't know, oddly frustrating. But it does, despite the name, it does actually have all of the constructors that we want. So it has now, which is this sort of strict value suspension, delay, which is lazy, async, fail. Fail is basically you want to put an exception inside of your task. So that's basically functionally, it seems like it's trending in a good direction. But because it was written 5 years ago, back in the Stone Age, it has a really weird implementation based on actors and like other curious things that we don't touch anymore. It's very, very, very slow. Very, very, very slow and inefficient. So it gets a justifiably bad reputation because of that implementation. And it still doesn't provide any abstraction whatsoever. It actually provides less abstraction than I/O because there is no lift task. So like you literally just have task, and it's a task. And this has led to a sort of systematic problem in the Scala ecosystem basically for the last 5 years, where everybody has to use task, and like if someone else comes along and has their own task that's better than the Scala Z7 task, you're kind of stuck because all the middleware frameworks had to choose one for you. So this is just a problem. And finally, it has really unsafe concurrency. Like really, really, really unsafe concurrency. And it carrots you to do things which are actually broken. And we'll see some examples of that in a second. But first off, a program. So this is what a program looks like with task, right? And remember we said task has all the constructors that we want, like now, delay, async, et cetera. So it sort of feels like this is on the right track. We should kind of see how it's working. So here we just print out like enter list of names, we read from standard input, we tokenize those names, and then we use this traverse function, which is like a completely generic function that doesn't know nothing. It doesn't know nothing. That was like incredibly American. It doesn't know anything about list or task or anything exciting like that. It's completely generic, and for each name we print out hello. And then at the end of the world we call unsafe perform sync because we have to run the effect. We can't just return a task to the runtime, and sort of everyone moves on with their life, right? But this is kind of a trivial program because it's not only is it just like reading from standard in and things like that, but there's no asynchrony here, right? Like most of the stuff that we do now that's actually somewhat interesting is probably going to involve asynchronous I/O because that's how you write things at scale on every runtime ever. So how do we do that with task, right? Well, it's going to look something like this. So here's a function that reads from an asynchronous socket channel. This is the Java 7 NIO library, which we use because the Java 4 NIO library is inscrutable and no one touches it. And we're going to construct an async task. And constructing an async task gives us a callback in the body of that constructor that we can then use and invoke. And when we invoke that callback, the task will be completed. This is sort of like promise, but lexically confined. And we just read from the buffer, register a completion handler, and then complete the callback with this sort of like arrow right thing that, if you've used Scalaz, it's like burned into your soul. And if you haven't used Scalaz, you're like, why did the Scala programmers use so many ASCII symbols? Writing to the socket channel is basically analogous, right? We take a byte vector and like we sort of turn it into a byte buffer and put it out on the channel and complete the handler and life is good. This is completely asynchronous, right? Like this is not going to block any threads, but it will block the flow of computation, it will suspend the flow of computation until the callback is completed. And then when we use these things, right, so we call the read from channel function the write to channel function, we can just sequence them into a for comprehension and everything is basically isolated from us. We don't see the difference between synchronous tasks, like the one at the top, and asynchronous tasks, like the reads and writes. So here we're just like reading, presumably a version from a channel that we connected to nothing. We decode that version, and if it's valid, then we read a SYN, write an ACK. If it's invalid, we just close the channel, right? So basic network I/O stuff, right? There's a bear trap kind of hidden in this, though, right? And this is a bear trap that like has infested a surprisingly large percentage of the Scala ecosystem, because there's actually a surprisingly large percentage of the ecosystem that is built on task because it's really useful. And the problem is that no one really asks themselves this question, and therefore everybody's code has bugs. So if you've used task or a framework that uses tasks, you probably have this bug. And the bug is this: what thread are we on? Like at this point in the for comprehension, what thread is this scheduled on? Does anybody know the answer? The answer is the NIO event dispatcher thread. Why wouldn't you want it to be on that thread? And this is horrific. Like, this is terrible. Like, the NIO event dispatcher thread is not a thread pool that you want to do anything with. Like, you want to get away from it as quickly as possible. But task is just going to, like, blithely leave us over there. And it's because of the way that async is implemented. So this doesn't get said enough in talks or in like blog posts or in GIST or anything like that. So I'm literally just going to digress for 2 slides, and we're going to talk about what the heck do you do with threads on the JVM, because no one knows how to do this. So thread best practice, number 1, divide your thread usage into 3 categories: CPU-bound computation that has no I/O whatsoever, blocking I/O, so legacy Stone Age frameworks like Java I/O that you have to use but you really don't want to. That's a separate class of computation. And then event dispatchers. This is your 3rd category. And then allocate a single thread pool for each of these categories, okay? Where the computation pool is going to be a work-stealing pool. You pre-allocate it. It's num CPUs in size, right? Because you're just doing computation on this, right? You're literally CPU-bound. Allocate it to the number of cores, unless you're on Travis, in which case, don't trust the number of cores, but that's a digression. Blocking I/O. Blocking I/O has to be an unbounded thread pool, which sucks, right? Like if you're a systems programmer, the word unbounded should kind of send shivers down your spine. But you have to make sure this is bounded at some higher semantic level, because the problem is that blocking I/O is going to eat a thread. You can't put that on a limited thread pool because you'll starve. So unbounded and caching, and really try not to do it very much. And then finally, event dispatchers, which are going to be really small thread pools. Like 1 thread works really well for most applications. Don't go above 4. High priority daemon threads. And just basically, like, you're going to try to keep your computation as confined to the appropriate pool as possible, right? So if you're doing some CPU computation, doing computation of any sort, it has to be on the CPU pool. If you're doing blocking I/O, put it on the blocking I/O pool. And obviously, when you're receiving some event, you're going to receive it on the dispatcher pool, and then you're going to thread shift off onto one of the other pools. The problem is that Scalaz 7 gives us basically nothing to make this easier, right? Now, this is an important thing, right? This is exactly why you deployed your application into production, and your throughput was like 40% of what you thought it should be, is most of the time like thread stuff. Task doesn't help us solve it. In fact, like I said, nearly the entire Scala ecosystem has this bug. Task does, even worse, give us a function which seems like it would solve this problem, because it's called fork, and it takes a thread pool as a parameter, and it doesn't work. It's like literally a trap. It does not do the thing that you think it does. And so that's bad. It's like worse than nothing. And this use case of like moving things around between thread pools is like literally the most common thing that you're going to do when you're doing asynchronous programming. Like, you have to be able to do it very, very easily. And like I said before, Scalaz task, like, while all of this is going on, is encouraging you to do really, really, really dangerous concurrency. And it's really, really dangerous because in Scalaz task, there is no functionality for resource management, okay? So resource management and concurrency are really inextricably linked concepts. If you're doing one, you have to get the other one right. And Scalaz task doesn't. So the Scalaz task basically gives us some functions that look like this, right? So we've got both and we've got race. Both takes two tasks, an A and a B, and gives us a single task that returns a pair A, B, just runs them in parallel, right? Race is kind of a little bit weirder, and it takes two tasks, A and B, and it races them against each other, and the first one that completes, it's going to return that result. So these are kind of the core primitives. Other stuff gets built on top of this. And these are both broken. And they're broken because in Scalaz task, there's no way to safely do something like this. So here we have a task that acquires a resource, and then we run it through the both function with a task that just immediately produces an error, right? And you can imagine this is something more complicated, where like the task on the right does something elaborate and then accidentally produces an error, right? Like something like that. The task on the right is going to shut down the task on the left when it produces that error, and it's just going to immediately return the error. But then the question becomes, where does the resource go, right? So if you happen to actually acquire the resource, where does it go? And the answer is into the ether, where presumably it will be garbage collected. The race also has a similar problem, right? If we acquire two resources, right, and race them against each other, one of them's going to lose, and it's just going to leak, right? You're just not going to be able to do anything with this. So, these are what Scalaz task encourages you to do with concurrency, and it's wrong. It's really, really wrong. And because it doesn't give you any ability to handle the resource management perils that come along with this, you get yourself tied in knots. So it's a step in the right direction. It doesn't provide us with thread control. It's the concurrency is broken because there's no resource management in the algebra. There's no resource management in the API whatsoever. So you can just like build yourselves into traps. It has a terrible implementation and no abstraction whatsoever. Like no type classes, no way to abstract over your definition of task. So are there any other options, right? Well, maybe we could do like cont t of free of function 0 unit a, which thanks to Brian McKenna we know is actually task, but no one would ever want to use that. Like this is a very confusing type to look at, and it's sort of surprising that it works. So clearly this is, while that semantically does the right thing, it's not actually what we want to do. Other frameworks have kind of stepped forward to try to fill this problem space. So FS2 and Monix are two streaming libraries in Scala. They both provide task implementations with resource management, with abstraction. This was kind of FS2's contribution to the space, as they, for the first time, defined what it means to be an effect, what it means to be, asynchronous, things like that, in a very, very general way. And they also, like both of these provide performance which is an order of magnitude better than Scala Z7. Monix in particular has a really, really, really fast task implementation. But both of them are kind of tied to this larger streaming library, right? Like if you're going to use Monix's task, you're probably going to have to use Monix's streaming. And that's probably not what you want. And especially since these abstractions that they define are very specific to those frameworks, they're not this general standardized thing. It's a little difficult to take advantage of them in a cross-framework way. So this was why, basically at the beginning of this year, I created the Cats Effect project. So Cats Effect defines an I/O monad, which we're back down to 2 characters. And the I/O monad has all the constructors you know and love. I bike shedded them a little bit because I'm like that. But it's basically all the same things as in task, right? We have pure, apply, async, and raise error. It is much, 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 much simpler on the inside. Like much, 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 much simpler. The implementation has no actors. It's really very straightforward code, aside from like one data structure. And it defines a set of abstract type classes and laws. So we'll talk about what laws are in a second, but basically this gives us the ability to talk about, again, in a Platonic sense, what is an effect? Like, what does it mean to be an effect type like I/O? And how can we be sure that these effect types are behaving appropriately? And there is no concurrency whatsoever. So this is maybe like a controversial choice, but Katz effect basically makes the argument that the I/O monad should be a primitive on which you can build concurrency stuff that's safe on top of it. But concurrency, like I/O itself, is not an appropriate type to be doing concurrency with. You should be doing concurrency with something else. That's the contention, right? And so in that vein, I/O doesn't provide any concurrency, it doesn't provide any resource management, and it doesn't provide any preemption. So every I/O action is atomic, either it runs or it doesn't, one of the two. And there's no sort of intermediate state. And so that provides you with a sort of a sane building block, a simple building block, that you can build higher level things on that take care of these problems for you, such as FS2, for example. So here's our example from earlier using task. Now we use I/O. Things are a little bit more concise because that's nice. But basically, it's kind of the same idea, right? We haven't actually done anything different. We can replicate our asynchronous program from earlier. And again, it looks exactly the same. We constructed these read things using the io.async thing. But you notice we've added one line to this, and it's this shift function. So we shift explicitly to the CPU pool. And we can just do this wherever we want. And this actually completely solves the thread shifting problem, right? As the name suggests, right? It just basically gives you an effect which moves you from one pool to another. Specifically, what it does is it relocates computation following its sequencing. Everything after it in the for comprehension will be on the pool you give, whereas everything before it might be on some other pool you don't actually know. It is the only thread-related function in the entire Katz effect library. And we did this because when we started doing prototyping with Katz effect, we discovered that nearly every real program needed this function, which is kind of the argument I made earlier, right? Like, you always, always, always want this. So we just baked it into the library. It's not actually a primitive, though. You could just define it yourself. It's literally just there for convenience. The definition of this function is like 6 lines. So I said, I'm running out of time, but I said that Katz effect defines some abstractions. It defines what it means to be an effect. And it does this through a hierarchy of type classes with very small font. The type classes in red at the bottom are things that are in Katz effect. And so we have sync and async and effect, and then we have the lift IO thing that we saw from earlier. But synchronous effects, asynchronous effects, and just regular effects, right? And we basically make the argument that synchronous effects are fairly common. Asynchronous effects are a specialization of synchronous effects. So like every asynchronous effect could be a synchronous effect. And regular effects, like total package effects down at the bottom, are this runnable thing that's a very tight specialization. So it's relatively easy to be a sync. Like basically, actually, all you need to be this is laziness and error handling. Like those two things, you're probably going to be fine. So like if you're familiar with Katz, there's this type in the library called eval. Eval is not a sync because it doesn't have error handling. But if you do either T of eval, it is a lawful sync. Async requires callback support, okay? So callbacks are kind of difficult to handle correctly, especially if you care about stack safety. So there's a lot fewer types that actually fall into this category. And then finally, the effect type class, like if you have an instance of effect, you are literally as powerful as I/O. Like you're basically an I/O monad right there. But there could be many different instances of this, right? So like Monix's task, the Scalaz at 8 I/O, like all of, and of course Katz effect I/O, like all of these are different instances of effect. But with all of these things, parametricity, like that argument that we made about monad earlier, isn't strong enough for us to sort of constrain the behavior of these type classes, right? Because the types are actually really general, right? You just like take a thunk and like put it inside a thing. That doesn't really tell you how that's supposed to behave. So what we need in order to prevent people from writing incorrect implementations is a set of laws, okay? And I don't mean the set of laws that you like write in LaTeX and then put on the Haskell wiki. I mean like actually a testable set of laws, right? Like actual code that basically produces a TCK for implementers of these type classes. And then once we've got this, users can rely on lawful behavior. Because as long as the implementers aren't doing something nasty, the users know that the implementers had to pass the TCK. They had to pass the laws. And so every instance that they receive that claims to be an effect is actually going to behave sanely. And implementers, meanwhile, can use the laws as like a free test suite, right? Like it's a bunch of tests. We worked very, very hard on it. They're actually somewhat hard to satisfy if you're doing things wrong. You can just toss them in your program and make sure that your implementation works. So here's kind of what they look like. This is sync laws, or a part of sync laws, rather. We've got some relatively straightforward laws here, right? Like if you delay a pure constant that you already have, it's the same as pure. That seems intuitive. If you throw an exception inside of delay, it gets caught and sequenced as an error. That's the last one down at the bottom. So these are all laws, and there's several more, and each of the type classes has its own laws associated with it. And if you're an implementer, you can, like for example, this either t eval thing, you can take these laws and you can put this in your test suite, and when you run it, like a whole bunch of tests are going to run with a bunch of different property checks, and they're going to verify that your implementation is not wrong. So this is how we can be sure that the instances are valid, that the instances are safe to rely on. It's how we can prevent invalid instances, like future, for example. Remember, we talked about how future is not really a suitable IO type, and the laws will tell us this. If we try to implement an effect for an instance of effect for future, running the laws will fail. Like the tests will find all of the flaws that we pointed out at the beginning. There's also some other ones that are kind of surprising, like the monad reader type, the reader monad transformer, Scalaz, has some issues as well. Specifically, it's not stack safe, right? And we said that stack safety is an important property of these things. Scalaz doesn't have it. Therefore, Scalaz of some effect is not an effect. So anyway, several frameworks already are using these abstractions and getting really good value out of them. So FS2, for example, we already talked about. Basically, if you use FS2, you don't have to use my IO type with it. You don't have to use Scalaz's IO type. You can use any IO type that you want. Monix's task, for example. Anything that satisfies the laws. And that is a very, very, very powerful concept. HTTP4S, which is like the only web framework you should think about in Scala, Doobie, and several other frameworks are also taking advantage of this. So it's kind of becoming a standard definition for what it means to be an effect in Scala. And like I said, if you don't like my IO, which I completely understand, you don't have to use it. You're free to use someone else's. So finally, in conclusion, effects are scary. Like always scary, all the time, terrifying. The IO monad is really, really, really helpful, and being generic about it allows very strong ecosystem effects. All of the options in Scala were bad before recently. They were really smart in their day, but their day was past, and now we write on paper rather than stone. So cat's effect, yay! Anybody have any questions? Do we have time for questions? No. We don't have time for questions. Angry Bodil is angry.
Give us some applause, thanks.